Top 25 Coding for Data Engineering Interview Questions and Answers. Welcome back to the channel. If you're preparing for a data engineering interview, especially the coding round, you're in the right place. Data engineering interviews are not just about theory. They test your ability to write clean code, handle large datasets, optimize performance, and think like a system designer. In today's video, we'll walk through the top 25 coding interview questions for data engineers with clear, real-world answers that interviewers actually expect. Let's get started and level up your preparation. 1. What is the difference between ETL and ELT? ETL stand for extract, transform, load, while ELT stand for extract, load, transform. In ETL, data is transformed before loading into the data warehouse, which is common in traditional systems with limited storage and processing power. ELT, on the other hand, loads raw data first and performs transformations inside the data warehouse. Modern cloud platforms like BigQuery and Snowflake favor ELT because they can handle massive processing efficiently. ELT also provides more flexibility for analytics and faster ingestion pipelines. 2. How would you remove duplicate records from a large dataset? Removing duplicates depends on the storage system. In SQL, we commonly use row_number with a partition and then filter rows where the rank is greater than 1. In distributed systems like Spark, we use drop duplicates or group by operations for large datasets. It's important to identify a unique key and minimize shuffling to improve performance. Efficient deduplication ensures data accuracy and prevents incorrect analytics or inflated metrics. 3. What is data partitioning and why is it important? Data partitioning is the process of dividing large datasets into smaller, manageable pieces based on a specific column like date or region. It improves query performance by scanning only relevant partitions instead of the entire dataset. Partitioning also helps with parallel processing, scalability, and cost optimization in cloud data warehouses. Without partitioning, queries can become slow and expensive, especially when working with terabytes or petabytes of data. 4. Explain how indexing works in databases. Indexes are data structures that improve query performance by allowing faster data retrieval. They work similarly to an index in a book, helping the database locate rows without scanning the entire table. Common index types include B-tree and hash indexes. While indexes improve read performance, they can slow down write operations because indexes must be updated during inserts or updates. Choosing the right index strategy is critical for balanced performance. 5. How do you handle missing or null values in a dataset? Handling missing values depends on the use case. Common strategies include removing records, replacing nulls with mean, median, or default values, or using forward and backward filling. In SQL, functions like coalesce help manage nulls. In data engineering pipelines, missing data should be logged and monitored to avoid silent failures. Proper handling of null values ensures clean datasets and reliable analytics. 6. What is a window function in SQL? Window functions perform calculations across a set of rows related to the current row without collapsing the result set. Examples include row_number, rank, and sum, over. They are widely used for ranking, running totals, and time-based analysis. Window functions are powerful because they allow advanced analytics while keeping row-level detail intact, making them essential for data engineering and reporting tasks. 7. Explain normalization and denormalization. Normalization organizes data into multiple tables to reduce redundancy and improve consistency. It is commonly used in transactional systems. Denormalization combines tables to reduce joins and improve read performance, which is common in analytical systems. Data engineers often denormalize data for reporting and dashboards. Choosing between normalization and denormalization depends on workload requirements, query patterns, and performance needs. 8. How does Apache Spark handle large-scale data processing? Apache Spark processes large datasets using distributed computing and in-memory processing. It divides data into partitions and executes tasks in parallel across multiple nodes. Spark supports batch processing, streaming, machine learning, and graph processing. Its in-memory model makes it faster than traditional MapReduce. Spark is widely used in data engineering for ETL pipelines and large-scale transformations. 9. What is the difference between batch processing and stream processing? Batch processing handles large volumes of data at scheduled intervals, such as daily or hourly jobs. Stream processing handles data in real time as it arrives. Batch processing is easier to manage and debug, while streaming enables real-time insights. Modern data architectures often use a hybrid approach to support both historical analysis and real-time decision-making. 10. How would you optimize a slow SQL query? To optimize a slow query, start by analyzing the execution plan. Add proper indexes, avoid unnecessary joins, and limit selected columns. Filtering data early, using where clauses improve performance. Partitioning and clustering can also help. Writing efficient SQL is a key skill for data engineers because poorly optimized queries increase costs and degrade system performance. 11. What is schema evolution and how do you handle it? Schema evolution refers to changes in data structure over time, such as adding, removing, or modifying columns. In real-world systems, data formats rarely remain static. Data engineers handle schema evolution using schema-aware formats like Avro, Parquet, or ORC, which support backward and forward compatibility. Versioning schemas, validating incoming data, and using nullable fields for new columns are common strategies. Proper schema evolution prevents pipeline failures and ensures older data remains readable while supporting future changes smoothly. 12. What is the difference between OLTP and OLAP systems? OLTP systems are designed for transactional operations like inserts, updates, and deletes. They handle a large number of small, fast queries and are optimized for consistency. OLAP systems are built for analytics and reporting, handling complex queries over large datasets. They focus on read performance and aggregations. Data engineers typically move data from OLTP databases into OLAP systems through ETL pipelines to enable business intelligence and analytics without affecting transactional performance. 13. How do you ensure data quality in a data pipeline? Data quality is ensured by implementing validation checks at multiple stages of the pipeline. This includes schema validation, null checks, range checks, and duplicate detection. Logging and monitoring are critical to detect anomalies early. Data engineers also use automated tests and data profiling tools. Maintaining data quality is essential because poor quality data leads to incorrect insights and loss of trust from stakeholders. A reliable pipeline always prioritizes data accuracy and consistency. 14. What is a data lake and how is it different from a data warehouse? A data lake stores raw, unstructured, semi-structured, and structured data at scale. It allows flexible schema-on-read processing. A data warehouse stores structured, processed data optimized for analytics and reporting. Data lakes are ideal for exploratory analysis and machine learning, while data warehouses are better for business intelligence. Modern architectures often combine both, using a data lake for raw ingestion and a warehouse for curated datasets. 15. How you handle late-arriving data in pipelines. Late-arriving data occurs when records arrive after the expected processing window. Data engineers handle this by designing pipelines with watermarking, reprocessing logic, or backfilling mechanisms. Partitioning by event time rather than ingestion time helps manage late data. Streaming frameworks like Spark Structured Streaming support watermarking to handle such scenarios. Proper handling ensures data completeness without disrupting downstream analytics. 16. What is idempotency in data engineering? Idempotency means that running the same operation multiple times produces the same result. In data pipelines, idempotent jobs prevent duplicate data during retries or failures. This is achieved by using unique keys, overwrite logic, or upserts instead of inserts. Idempotency is critical for reliability, especially in distributed systems where failures are common. Interviewers look for this concept because it reflects production-ready thinking. 17. Explain the concept of shuffling in Spark. Shuffling is the process of redistributing data across partitions during operations like joins and group by. It is expensive because it involves disk and network I/O. Excessive shuffling can significantly degrade performance. Data engineers reduce shuffling by using proper partitioning, broadcast joins, and filtering data early. Understanding shuffling is essential for optimizing Spark jobs and managing large-scale data efficiently. 18. What is a slowly changing dimension, SCD? Slowly changing dimensions refer to data that changes slowly over time, such as customer addresses. Common types include Type 1, which overwrites old data, and Type 2, which keeps historical records using versioning. Data engineers choose the appropriate SCD type based on business requirements. Handling SCDs correctly is crucial for accurate historical reporting and analytics. 19. How do you manage failures in data pipelines? Failures are handled using retries, alerts, and checkpointing mechanisms. Data engineers design pipelines to fail gracefully and resume from the last successful state. Tools like Airflow provide task-level retries and monitoring. Logging detailed error messages helps with debugging. Reliable pipelines anticipate failures and include recovery strategies rather than assuming everything will work perfectly. 20. What is a primary key and why is it important? A primary key uniquely identifies each record in a table. It ensures data integrity and prevents duplicates. Primary keys also improve query performance when indexed. In data engineering, choosing the correct primary key is critical for joins, deduplication, and incremental loading. Interviewers often ask this to test understanding of relational data fundamentals. 21. Explain the difference between inner join and left join. An inner join returns only the records that have matching values in both tables. If there is no match, the row is excluded from the result. A left join, however, returns all records from the left table and only the matching records from the right table. If no match exists, null values are returned for the right table columns. Data engineers must choose joins carefully, as incorrect joins can cause data loss or duplication, which directly impacts reporting accuracy and analytics results. 22. What is data skew, and how do you handle it? Data skew happens when data is unevenly distributed across partitions in a distributed system. This causes some tasks to process significantly more data than others, slowing down the entire job. Data engineers handle skew by increasing partition counts, using key salting techniques, or applying broadcast joins for smaller datasets. Identifying skew early through monitoring and query analysis is essential. Proper skew handling improves performance, reduces execution time, and ensures efficient resource utilization in systems like Apache Spark. 23. How do you perform incremental data loading? Incremental data loading processes only new or updated records instead of reloading the entire dataset. This is usually achieved using timestamps, version numbers, or change data capture techniques. Incremental loads significantly reduce processing time and system costs. Data engineers implement validation checks to ensure no data is missed or duplicated. This approach is critical for large-scale pipelines where full reloads are impractical and inefficient. 24. What is the role of orchestration tools like Airflow? Orchestration tools like Apache Airflow manage and schedule data pipelines. They allow data engineers to define workflows as directed acyclic graphs, manage dependencies, handle retries, and monitor failures. Airflow improves reliability and visibility by providing logging, alerting, and task-level control. These tools are essential in production environments where multiple pipelines run daily. Interviewers often ask about orchestration to assess real-world pipeline management experience. 25. Why is coding skill important for a data engineer? Coding is a core skill for data engineers because they build, optimize, and maintain data pipelines. Strong coding enables efficient data transformations, error handling, and performance tuning. Languages like Python, SQL, and Scala are commonly used in real-world systems. Coding skills also help data engineers automate workflows and integrate multiple systems. Interviewers look for candidates who can write clean, scalable, and maintainable code that performs well under heavy data loads. And that wraps up our top 25 coding interview questions for data engineers. If you understand these questions and can confidently explain the answers, you'll be well prepared for most data engineering interviews. Remember, interviewers don't just test knowledge, they test how you think and solve real-world problems. If you found this video helpful, Don't forget to like, subscribe, and share with others preparing for data engineering roles. See you in the next video, and best of luck with your interview preparation.